Many interesting things happened during the 1980s. One of those things was the launching in 1983 of a large randomized trial on folic acid and birth defects. This was the MRC vitamin study, which included women from 33 countries who were planning to get pregnant. Amazingly, the risk of neural tube defects, a type of birth defect, was reduced by 70% in the group assigned to folic acid. And this was a big deal because neural tube defects are serious birth defects that happen when the central nervous system does not close in the first 28 days of pregnancy. And this lack of closure can lead to very serious disabilities or death. So the findings from the trial were used to support major changes in public health policy. In the United States, the Centers for Disease Control advises that all women should take 0.4 milligrams of folic acid every day before getting pregnant. And many countries have implemented mandatory fortification of wheat flour with folic acid, so women can get their daily dose of folic acid from their food. However, the MRC vitamin trial left some questions unanswered. First, the study only included women with history of pregnancies affected by neural tube defects. So, would folic acid work for the rest of the women? And second, the study gave women high doses of folic acid. Would the same effect be seen with the lower and possibly safer doses that were usually included in multivitamin supplements? Since no randomized trials were available to answer these questions, investigators did what they always do. They analyzed data from observational studies. And one of those studies was the Sloan Epidemiology Unit Birth Defects Study at Boston University. This observational study included pregnancies from several North American cities in the 1990s. And this study estimated that the risk of birth defects was 35% lower among pregnancies exposed to folic acid. 35% lower. That's a strong association. Can we then conclude that folic acid at the usual doses lowers the risk of neural tube defects by 35% in normal women? Or maybe more educated women take more vitamins and also do other things that reduce risk of birth defects. If that is the case, then we would expect to find a lower risk of birth defects in folic acid users, even if folic acid had no effect on the risk of birth defects. Or it might be the other way around. Maybe women with a history of birth defects take more vitamins, and these women are at a higher risk of having a baby with birth defects. If that were the case, then our analysis would underestimate the beneficial effect of folic acid on birth defects. Folic acid might reduce the risk by, say, 50%, but because the high-risk women are more likely to take folic acid, we only see a 35% lower risk. Like any observational study, this one may be affected by confounding, which means that in our analysis, we will need to adjust for variables like education and prior history of birth defects. And in particular, it turns out that there is a variable L in our dataset. And if we adjust for L, the estimate moves from a 35% reduction to only a 20% reduction in risk. That's a big change. So do we need to adjust for L then? What is the closest to the true effect of folic acid? The unadjusted estimate of 35% lower risk, or the L-adjusted estimate of 20% lower risk? Questions like this arise constantly in research studies. And by the end of this lesson, you will know how to handle these questions. You will be able to explain under which circumstances you would want to adjust for the variable L to quantify the effect of folic acid on the risk of neural tube defects.